Greetings, Biz2A students. After thinking about how fast our discussions went this week, I wanted to give everyone the chance to learn the material in a bit more in depth than what we were able to go in discussion. That just has to deal with the very quick discussion we had to have, especially being condensed down due to all the administrative stuff we had to take care of. And so my goal with this is just to sort of go a lot slower, go a little bit more in depth instead of just brushing over everything. My goal is to be able to add timestamps throughout this video so that you can jump ahead to the sections that you need. How far I will get along with that, I don't know. Depends on how long this takes me. It's currently 10:45 p.m. on January 8th. Hopefully I finish before January 9th. Regardless, let's get started. We're going to start with the very, very basics of sort of the three components of our atoms, just as we did in lecture. Okay, so atoms, I don't know why there's a Grammarly thing on my screen. That's slightly annoying. Anyways, atoms are primarily composed of three things, right? Now, depending on how detailed you get, you can go way further, start talking about quarks. That's well beyond what we're going to discuss. So we are just talking about the direct three things that produce our atoms. And they are our protons, neutrons, and electrons. Okay. Our protons will often be abbreviated, P+, neutrons, N0, and electrons, E-. This also reflects their charge. So if we were to sort of make a little table here and we added the charge of each of these guys, we would say that protons have a +1 charge, neutrons are 0, and electrons are -1. We can then also look at their location within the atom. So if we quickly move down here to the Bohr model of the atom, okay, what we have is we have the nucleus in the middle surrounded by our electron cloud. So here is our nucleus. Here are our electron clouds or electron shells. Okay, putting this into our table now, the location within the atom of each of these guys. The protons are in that nuclear core, so the nucleus. Neutrons, also in the nucleus. And our electrons are in their electron cloud, or the electron shells. Okay. Finally, we can look at what these things determine. So in other words, the number of protons, for instance, this determines the atomic number, which determines the element. So elements are defined by the number of protons in the nucleus. The neutrons will affect the mass of a specific element. In other words, the isotope. Isotopes are elements, the same element with different atomic masses due to different numbers of neutrons. And electrons will affect the chemical behavior of our atoms, including bonding. We're going to return to bonding in just a bit. But this is sort of the first thing we need to get down, especially paying attention to our elements and bonding. Now, because I'm not about to draw a periodic table from scratch, I pasted one in here. This is not mine. Once again, I will always tell you if something is not mine. That way you know if it doesn't look good, it's not my diagram, and all the really good ones are my own creations. Okay, so when we're looking at this periodic table, we see all these different sort of letters and numbers. Okay, they mean different things. Let's hone in on carbon for a second. Carbon with a 6 above it. This 6 is referring to the number of protons. So what this means is every single carbon atom in the nucleus has 6 protons. If it does not have 6 protons, it is not a carbon atom. Additionally, our carbon will be referred to using the letter C, as opposed to writing out carbon in its entirety. This is too long. We need a very fast way to describe it. All right. Next thing is we can pay attention to the group number at the top and the period to the left. The group will tell you how many valence electrons. So group is the number of valence electrons, VE minus, in that column. What do we mean by this? Okay. Well, oftentimes, instead of saying it 1 to 18, what you often will see is 1A, 2A. We will ignore the metals for now, and then it will pick up with 3A, 4A, 5A, 6A, 7A, and 8A. This is referring to the A group, which are the main group. Okay, everything that happens here are the transition metals, and they get quite complex with what they do. You will learn more about these sorts of things in Biz 102 when you start talking about cofactors, especially looking at things like iron, copper, and what's another good one? Yeah, iron and copper for now. Sometimes you'll see the other associated ones scattered around. Okay. Anyways, back to our main group. So what that tells us is all of the atoms in the 1A column or the 1A group will have 1 valence electron. For example, sodium over here has 1 valence electron. To draw its Lewis structure, we put its symbol in the middle, and we draw the number of valence electrons surrounding it. That's 1. Now, we've been saying we've been using this term valence electron, but really what is that? And we can define that quite easily. So valence electrons are the electrons in the outermost electron shell. In other words, these are going to be the ones used in bonding. Okay? That is about as specific as we're going to go. We won't talking about anti-bonding orbitals, bonding orbitals, none of that. We're just going to run with valence electrons are going to be the ones we look for to determine bonding. Okay? For our purposes in this class, we want to pay attention to 6 primary elements. They are carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. For each of these, we want to determine the number of valence electrons. So what we do is we look to the periodic table and we start counting. We start at 1 for hydrogen. This is 1 electron as well. Here's 2 electrons for helium, 3 for lithium, 4 for beryllium, 5 for boron, and 6 for carbon. However, not all of these are valence electrons. We are only looking for the outermost shell. So what we do is we look for the period number, and we want to find the period where that element resides. So carbon sits in the second period, so we will be counting only the second period electrons to determine the valence electrons. The first period electrons will be sitting in the first shell, and they will not be partaking in bonding for the purposes that we care about in Biz 2A. So we count starting from the left with lithium. There's 1, here's 2, 3 for boron, and 4 for carbon. So that tells us that carbon has 4 valence electrons. Hydrogen, we have to scroll all the way back, and we see hydrogen has 1 proton, which means it also has 1 electron. So hydrogen has 1 valence electron. oxygen. Once again, it is second period, so we count 1, 2, 3, 4, 5, and 6. Nitrogen is 1, 2, 3, 4, and 5. Phosphorus now is in the third period, so we start with sodium. We go 1, 2, 3, 4, and 5. Notice how both nitrogen and phosphorus both have 5 because they are in the same column or same period. Or same group. Sorry, not same period, same group. Finally, we get to sulfur. We can see it's 1 away from phosphorus, so we should be adding 1. And it should also have the same number of valence electrons as oxygen. So it makes 6. Now, we can start to figure out how many bonds these guys will form. Let's use carbon again as our example. So carbon has 4 electrons. Drawing its Lewis structure, we say 1, 2, 3, and 4. What we have to remember or learn about is what's called the octet rule. Elements, in this case, under the octet rule, elements achieve stability when they reach a full outermost electron shell. For most elements, that is 8 electrons. Most shell, and this yields to stability. You will find that this is not always true, and we will talk about it when we look at hydrogen. So, for carbon to bring in 4 more electrons to achieve a maximum of 8, it needs 4 more electrons. Well, where's it going to get it from? It can't just pick it up from the environment. Well, someone has to bring it. And that's exactly what happens. So we need to add in another electron from some atom. Who's to say what it is? Maybe another one from another. Third. And a fourth. Now, when this happens, carbon is not just taking these, it's actually sharing. So even though it is now getting 8 electrons, it has also donated its 4. And perhaps we can use hydrogen as our good example because hydrogen only has 1 valence electron. So perhaps each of these came from a hydrogen atom donating in its electron. So how we would now draw this in the Lewis structure, in its correct Lewis structure, we'd have our carbon surrounded by our hydrogens, and each of them is sharing 2 electrons. So carbon has given each hydrogen an electron, and each hydrogen is giving carbon 1 electron. Now, the reason why hydrogen can do this is because it is a period 1 element. The maximum number of electrons within this shell is 2. So it does not have the octet rule. Okay. So if we were to then put this into bonds, we would say every single bond gets 1 line. So we draw a horizontal line like that, vertical line to the next hydrogen, horizontal line, and our 4th horizontal line. And now we have just created the molecule methane. Its name is not important. So, using that logic, we can ask ourselves, well, how many bonds does carbon need to reach its octet? And as we've just described, it is 4. Same thing with hydrogen. It only needs 1 bond. Let's look at oxygen now. Oxygen has 6 valence electrons. And we can use hydrogen as our electron donor again. Each hydrogen will bring in an electron to the party. yielding us our good friend dihydrogen monoxide, aka water. And as we see here, oxygen now has its 8 electrons, 2 in this left-hand bond, 2 in the right-hand bond, 2 in what's called a lone pair, and 2 in the bottom lone pair as well. 2 plus 2 plus 2 plus 2, get out a calculator, does in fact equal 8. So oxygen will make 2 bonds. Sometimes you will see it make only 1 bond, in which case it will have a negative charge. Why is this the case? Well, let's take a quick tangent and look at that. Suppose one of these hydrogens gets taken off by something else. What we're left with is a hydrogen attached to our oxygen, and because the hydrogen was stolen but left its electron, those two, the one that oxygen gave it and the one that hydrogen gave the oxygen, are left behind. So now, oxygen has 3 lone pairs and 1 double bond. We can now calculate a formal charge on this. And to do that, we take the number of electrons, or sorry, not the number of electrons, the I'm dying. The number of valence electrons, and subtract from it the number of electrons actually surrounding this oxygen. We count 1 for every single, lone pair, or electron in the lone pairs. So here's 1, here's 2, here's 3, here's 4, here's 5, and here's 6. And then we count 1 per covalent bond. So here would be 7. So it has 6 valence electrons. It now has 7 electrons surrounding it, yielding us a -1 formal charge. So we would draw it like this. Actually, we'll leave that out for now. Like that. And this is known as a hydroxide ion. We will learn more about this later. So, we've seen that oxygen can do this. It can also form 3 bonds, in which case it carries a positive charge. However, we will not come across this in Biz 2A. When you start taking organic chemistry, you will learn about it, and then it will carry on in our upper division biology classes when we start talking about biochemistry. Moving on to nitrogen. Nitrogen, well, if we were to draw it out again, it has 1, 2, 3, 4, 5, and so it needs 1 bond with a hydrogen, 2 bonds with a hydrogen, and 3 bonds with the hydrogen to get to our octet. So it has 3 bonds. However, nitrogens have this cool thing with this lone pair, where it can actually pick up a hydrogen in the environment, just a proton. When you see electrons in a lone pair, an arrow or a squiggly line with an arrow at the end, this is saying these are what the electrons are doing and where they're moving. So what this is showing you is these 2 lone pair electrons are picking up this proton from the environment. And now we have a nitrogen connected to 4 hydrogens. If we calculate its formal charge, it has 5 valence electrons, and if it only gets 1 electron per bond, that yields 4, giving us a +1 charge. This is why this functional group can protonate and deprotonate. We will talk about this near the end of this video. So nitrogens can sometimes form 4 bonds. Phosphorus, just like nitrogen, can form 3 bonds. However, it can also do something funky, where it forms 5 bonds. We will see this when we discuss the phosphate functional group. Sulfur, just like oxygen, can form 2 bonds. Sometimes you will see it form 1 bond. just like oxygen. However, it can also form 6 bonds. We will see this when we discuss sulfates. However, that is not something we generally look at in this class, so store this away for more advanced biology, cell biology, and biochemistry courses. So this takes us through our core elements. These you should have memorized, along with the number of valence electrons and the number of bonds they form. And in which cases do the elements become charged or not. This will be very, very helpful when we start talking about functional groups. So we've gotten our elements out of the way. That was our sort of first piece of this puzzle up here. Now we want to start talking about bonding, because we've been building up this whole thing about valence electrons and bonds, and so that's what we want to focus on next. Okay, so our guiding question is based around this idea of, are all bonds treated the same? And the answer is no. There are multiple different types of bonds, and our goal is to be able to predict the bonds formed based on the properties of the elements involved within those bonds. So, we can start perhaps with this idea of if we have some amount of electrons moving between our elements, there's 2 primary ways that they can go. Think of it like you and I are talking to each other, and one of us has a candy bar. Now, we could split that candy bar, or I could give you that candy bar. That is exactly how elements work. So, when we're discussing the types of bonds, we have 2 primary that we are looking at. First one are our covalent bonds. And covalent bonds are the sharing. Okay? So this is you and I sharing that candy bar. However, if I decide to give you this candy bar, because maybe you really, really need it, and I just did biohazard in my lab, so I'm not, particularly hungry, maybe I give it to you, and that represents our ionic bonds. So this is the transfer of electrons. Now, this isn't the full story, because really this just sets up charges. Charges, as we just outlined previously, these sets up charges that then interact in what's called an electrostatic interaction. All right. So now we need to figure out, well, what is going to be the deciding factor of these? How do we get some bonds to share and some of them to transfer? Well, to answer this, we're going to look to sort of how badly our atoms want their electrons. And that brings us into this idea of electronegativity. Electronegativity references we can say the tendency of an atom to, we could say, pull or attract shared electrons. In other words, this is how strong an atom or an element pulls on the electrons involved in its bonds. All right, so if we have a covalent bond, they're sharing electrons, which means that maybe one is pulling, it really wants those electrons, but that other atom isn't giving them up. So they find a compromise where they share the electrons. In the ionic bonds, what we're saying is, okay, one is really, really, really pulling, the other one doesn't care so much. And so that pull from the electron, or the atom that really wants this electron, is enough to take it from the other one, establishing our charges. So what this tells us intuitively then, or using that logic, maybe it's not intuitive, but using that logic, we would expect a large difference in electronegativity between our two atoms involved in the bond. Remember, one is really, really pulling and just yanks that electron away from the other. On the contrary, we would expect the covalent bond to not have a large difference, or not as large of a difference, relatively speaking. And now we're able to distinguish between our covalent and ionic bonds. If we see a very large difference, maybe something like sodium and chloride, we're thinking ionic bond. If we see a very small difference, we're thinking a covalent bond. But what about in the middle? Well, we can't really account for that for these two types. And so we can ask ourselves, well, when we share, does it have to be equal? Well, what if you and I, once again, we're sharing a notebook, and you're taking Biz 2A, where you have a lot of notes, and I'm taking underwater basket weaving. Well, I don't really have a lot of notes. Should we share that notebook equally? Or perhaps should you have more of that notebook dedicated to your work, and I have less? And the latter seems more fair, right? I don't need a lot of space in that notebook. Maybe I need just a couple pages. And you need a large chunk of that notebook in order to write all your Biz 2A notes. So within the sharing, we have two cases. We have equal sharing, and we have unequal sharing. So in equal sharing, if we go back to sort of our idea about how much pull there is, what that's saying is one of our atoms is pulling a lot, or maybe a little, but that other atom is pulling with the same ability or force. And what that means is those electrons aren't going to be biased to any one side. In other words, pulls or differences across the sides are not generated. So we conveniently name this a non-polar covalent bond. Okay, but now if we're doing unequal sharing, right? I haven't completely given you this notebook. I'm still using part of it, but you're using the vast majority of it. In other words, this notebook has sides to it, right? It's not just split right down the middle. In other words, we've created poles. So this is named a polar covalent bond. All right. So we now have this setup. We have non-polar covalent bonds. We're thinking, very similar, approximate ENs between the two. Maybe a slight difference, or we can just say a medium difference. Medium difference, otherwise known as delta, in the electronegativities, and then finally a large difference. But you'll notice in science, small, medium, and large are quite vague terms. And oftentimes, like in statistics, we want to ask, how large does something have to be to actually make a difference? And there's numerous statistical tests that you will get into when you take stuff like Stats 13 or Stats 100. It's very, very interesting and serves as the foundation for science. So what that means is we need a way to quantify this. Now, we're not going to be running any statistical tests. Don't need to use R, or because I'm in epidemiology, I learn in SAS, or I use SAS as my programming tool. Instead, we have some cutoffs that people before us came up with. Okay, so our two cutoffs are approximately 0.4 and somewhere around 1.8, 1.9. It sort of depends on the exact scale you use. We'll go with 1.9. If your professor gives you an exact value, or whatever values your professor gives you in lecture are the ones you should default to. The reason why these numbers change is they are based on a scale. They are not absolute. So these are relative values and therefore can change based on what you define as sort of your primary point for basing your calculations. Now, anything less than 0.4, that's a pretty small difference in En, right? So if we calculate the En, so the En of our first atom minus the electronegativity of our second atom, if we get a small difference, that means they're approximately equal. So that sounds like our nonpolar covalent bond. Okay, what about a medium difference, right? It's a little bit more than 0.4, maybe 0.6, 0.7, somewhere around there. But it's not super high. Well, that sounds like our polar covalent bonds. And then finally, it's super high, right? One is really, really wanting those electrons, and the other one doesn't care. That's our ionic bond. Note that you should generally take the absolute value of this, so you end up with all positive values in this calculation. All right, so now we have a way to predict, given the electronegativities, the type of bonding that two elements will engage in. But we have yet to actually establish what our electronegativities are for our 6 elements. So if we move back up to our table here, we can add in one final column that looks at the electronegativities. Now, once again, you will find multiple values, and I personally am not a huge fan of memorization. If your professor tells you to memorize, then you should. However, I think it's better to understand conceptually which ones are the more electronegative atoms. A lot of things go into electronegativity. For our purposes, what I want you to know is electronegativity increases going up and to the right. What that means is fluorine, not helium though, fluorine is our most electronegative element at about 3.98 on the Pauling scale. What you'll notice is right next to it is oxygen and nitrogen. Fluorine is not relevant for our class. You might talk about it later on in biochemistry and physiology, but for us, we're not going to talk much about it. Instead, we're going to focus on our 6 here. And so, as I said, nitrogen and oxygen are one of our 6, and they are quite electronegative. Specifically, our nitrogen is about 3-ish, and our oxygen is about 3.4-ish. I believe it's 3.44 and 3.04. Okay. On the other hand, hydrogen and carbon are not that electronegative. Carbon is about 2.5, and hydrogen somewhere around 2.2. Phosphorus also around 2.2 with hydrogen, and sulfur is somewhere around 2.5 with carbon. Somewhere around there. What you should, once again, remember is that oxygen and nitrogen are our 2 most electronegative ones. So they will be the ones that are often the culprits producing our nonpolar bonds. So now with this, we can start to establish what are our polar and our nonpolar bonds. I would recommend going through this and showing yourself the calculations, but for right now, I'm just going to list out the primary polar bonds that we see in this class. They start off with oxygen bonded to hydrogen, oxygen bonded to carbon, nitrogen bonded to hydrogen, and nitrogen bonded to carbon. There are other polar bonds, oxygen and phosphorus as well. That's very, very important when we start talking about nucleotides and phosphate transfers. We will talk about nucleotide polymerization later on. Phosphate transfers, the energetics of it is a lot more biochemistry oriented. So when you take a class like Biz 103 or Biz 105, you will get to learn about it then. It's very, very interesting. All right, our sort of main non-polar bonds are definitely the carbon-carbon and carbon-hydrogen bonds. These are our main non-polar. All right, so we've now been able to identify polar and non-polar bonds. And now we want to look at the applications of polarity. And we have two primary ones. Applications of polarity. That is not a straight line. Close enough. Our first one is molecular polarity. So now instead of just looking at polarity within a bond, we're looking at polarity in a molecule. Now, before we can quite talk about molecular polarity, we also need to talk about dipoles. So we're going to pop back up here. I meant to talk about it earlier, and I forgot. I'm sort of running off my brain right now. So sometimes things get a little jumbled. My apologies. Let's look at the oxygen-hydrogen bond for a second. Oxygen is going to pull electrons more. So we can denote that by putting a large electron cloud around our oxygen. Hydrogen is going to have a small, or is not as large of a pull. So when the electrons go over there to the oxygen, they spend less time around hydrogens. Note that eventually you will talk about how these electron clouds are really a statistical model. So when we're saying that the electrons are more often found around oxygen, what we're saying is they're more likely, based on statistics, to be around the oxygen at any given point in time. And so that creates this sort of shape that you might have seen where we're looking at the electron densities. Larger cloud means there's more statistical probability of that electron occurring here. Okay? Now, because we're bringing all these negatively charged electrons to this side, we are bringing, well, more negative charges. But it's not a full negative charge, right? Because it's not like we have gained a full electron. Sometimes that electron is on the hydrogen side. So while sometimes, as we discussed up here, we can get a full negative charge when there's a transfer, this one, because it's not quite a transfer, we end up with a partial negative. So this oxygen, because the electrons generally are found next to it more often than the hydrogen, it gets a partial negative. Around the hydrogen, it gets a partial positive because it's losing some of that negative charge, and what's left is the positive charges of the protons. So you can either denote the polar bonds using a partial negative and a partial positive, or you can use dipole notation. How to do this? You put a line above or below, draw an arrow going to the side where the electrons are going, so in the direction of the arrows of the electron movement, and on the side where you would expect that positive, partial positive, you add a little positive. That is dipole notation. Now that we understand dipoles, we can now look at molecular dipoles. So molecular polarities are going to be based on the presence of molecular dipoles. Now, there's two things that we generally need. There are a few exceptions to this that we're not going to talk about. If you get curious, look up the molecule ozone, which is composed entirely of oxygen. It's O3, but possesses a molecular dipole. It's very, very fascinating, but it is outside the scope of our class. For us, we need polar bonds. Okay? In other words, let's say we have the molecule benzene. Benzene is composed entirely of carbon and hydrogen. Now, how did I know that? Because this does not look like carbon and hydrogen. Well, this is what we call bond line. And as we start to build molecules, as we're doing now, we want an easier way to show these molecules. That's where bond line formula comes in. Note how fast I drew that benzene. Now let's draw it in what's called calculi, which is our main sort of notation that we're used to. To draw this out, we need to make a ring of 6 carbons, add in our double bonds, and finally add in our hydrogens. Now, benzene's a fairly simple molecule structurally in terms of our purposes. Once you start learning about aromatics, it becomes quite a bit more complicated. But notice how long it took me to draw that out and how much more space it's taking. That's where bond line comes in. So how to convert calculi to bond line? Every single carbon becomes either a point or a vertex. Similarly, we can look at something like butane, which is 4 carbons, and we can see how, okay, every single carbon should be a point or a vertex. So there's 1 carbon, there's 2 carbons, 3, I want to get these more or less lined up, 2 carbons, 3 carbons, and 4 carbons. Just as we've done with the carbons in benzene. Now, because we know that carbon must form 4 bonds, but we've only drawn 1 bond, what that means is all other bonds must be taken up by hydrogen. So this carbon at the end has 1 bond explicitly drawn. That's this guy here. Well, we know it needs 4, and 4 minus 1 is 3. So that means this guy is attached to 3 hydrogens. If we look at this next carbon here, it has 2 bonds explicitly drawn, and 4 minus 2, because it needs 4 bonds, yields 2 hydrogens. This is the same for the hydrogen or the carbon next door. And finally, this carbon at the end once again has 1 explicit bond, and so the rest are taken up by hydrogens. Now, when you start to add in more heteroatoms, including oxygen and nitrogen, they will be explicitly drawn in. Let's take propanol. Yes. Propanol. Whew, it's been a while. Propanol has 3 carbons and 1 oxygen and hydrogen. Once again, we have carbon, 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 and then we have our oxygen. Now note that we have drawn in the hydrogen because it is part of this functional group. However, we've removed the bond between it and oxygen. It is still there, but it has been condensed. All other hydrogens will be operated on the same way we've been discussing. Finally, you might see a bond line structure where you see CH3 actually drawn out. For example, here's the amino acid valine. Note how the 2 terminal methyl groups are explicitly drawn. What this is saying is this carbon is covalently attached to this carbon here. This is because this is a methyl functional group that we will talk about later. However, it is generally also acceptable to draw this in bond line formula like that, where once again, these terminal groups are carbon with 3 hydrogens attached, exactly what's drawn here. So now that we've gotten a better way to draw molecules, we can return back to our molecular polarity. Now we need polar bonds. If we return back to benzene, it only is composed of carbon and hydrogen bonds. So it only has nonpolar bonds. We would expect it to be nonpolar. However, if we have polar bonds, let's consider our alcohol here for a second, propanol. While we have some nonpolar components here, we do possess a molecular dipole. Also, I treated this as a hydrogen or a carbon. I sincerely apologize. It should look like that. All right. If we notice, this oxygen should have a partial negative. The hydrogen has a partial positive, and this carbon has a partial positive. So we end up with a dipole on 2 bonds. And we have to make sure that these dipoles don't cancel each other out. If they do, it's like trying to pull in one direction and pull in the other direction at the same time. With equal strength, they cancel each other out. I will show you an example of that in a second. But in this case, due to the molecular polarity, if we were to draw this out more explicitly, the molecular geometry of this is where the dipoles actually sum together. For an overall molecular dipole, that looks like that. So this would be a polar molecule. So besides polar bonds, we also need to look at molecular geometry. To really illustrate why molecular geometry matters, we can look at carbon dioxide. Its structure looks like this. If we were to draw in our dipoles, we will have one there and a second one on the right side. Notice how they cancel each other out. They do not sum together. This one is pulling in this direction with the same amount as this pull in the other direction. If you've ever tried to move something where one person is pulling in one direction, the other one is pulling in the other direction, and you're pulling with the same amount of force, it does not move. So even though this possesses polar bonds, this is in fact a non-polar gas. Now, once you start talking about physiology and biochemistry, this becomes very, very important. We breathe out, or we produce carbon dioxide as a part of our metabolism. We will learn a little bit about this in somewhere around week 5, week 6. And this creates issues, but it can also be very, very helpful depending on the type of metabolism you're doing. When you take classes like Biz 102 or Biz 103, you will learn about how the body not only produces carbon dioxide, but also uses carbon dioxide, and all the carbon dioxide that doesn't get used, how hemoglobin and the red blood cells help transport that from where it's produced in the body to your lungs to be exhaled. As you guys hopefully remember from sort of the first 20 minutes of my discussion, is I really tried to highlight where the stuff we're learning in Biz 2A matters for more advanced courses. And one of those is physiology. All right, returning back to our applications of polarity. We now have molecular polarity, so we have nonpolar and polar molecules. However, we can also describe these in a different way. Polar molecules can also be classified as hydrophilic, meaning they love philic, water, hydro. Or they do not like nonpolar things, often lipids. So lipophobic. Phobic meaning fear of, lipo meaning lipids, which are nonpolar macromolecules. We will discuss that in just a little bit. Nonpolar molecules, ditto mark means repeat above, so that means molecules. Also known as, well, if polar molecules like water, nonpolar molecules probably don't, so they're hydrophobic. Or lipophilic. But why would this be the case? Let's examine a sort of basic example. Let's look at Actually, I'm going to draw it the other way. Let's look at methanol. Okay. Methanol does have this small methyl group, which would be nonpolar. However, this OH group is quite polar, right? If we were to calculate it, is a significant difference. This oxygen has a delta negative, hydrogen has a delta positive, and carbon has a delta positive. This is a polar molecule. Now, if you just have charges by themselves, they're actually not that stable. They need something nearby to stabilize them, which is exactly what happens in an ionic interaction. Let's look at sodium and chloride really quickly. Sodium has 1 valence electron, chloride has 7. We would take one of these electrons, that's a half arrow representing the movement of 1 electron, and we end up with Na plus because it is lost an electron, so it has 1 more proton than electron, and chloride has a negative charge because it has 1 more electron than proton. By itself, this is not very stable. However, because this positive and negative charge are nearby in an ionic interaction, they are actually stabilizing each other. To understand this, you do need to take a bit of physics and understanding how charges operate. For our purposes, we just need to know that when you have opposite charges like this, they stabilize each other. Remember how bonds stabilize? Same thing with our ionic interactions. Technically, an ionic is not really a bond. It's not really an ionic bond. It's more of an ionic interaction, but that's a soapbox moment for another day. This one is an extreme example, right, involving full charges. Back to our methanol, even though this doesn't have full charges, it is still partial charges. And so they need stabilization by other charged things, including other partial charges. Well, where can we get that? Well, one of them is water. Remember, water is set up. Here we have a partial positive, partial negative, or partial positive. So these guys can interact where this partial positive on the hydrogen is interacting with the partial negative on the oxygen, and the partial positive on this hydrogen is interacting with the partial negative on the oxygen. This is why polar molecules are hydrophilic. They love water and other polar molecules because they can form electrostatic interactions that are stabilizing. Now, if we put this next to benzene again, as cool as benzene is, although it is a toxin, no electrostatic interactions can take place here. Notably, this is not repulsion. Repulsion occurs when 2 charges of the same charge are in close proximity. So if we had 2 chloride ions right next to each other, these negative charges, when they get close, there is actually a force that separates them. There is no such separating force with hydrophilic molecules and hydrophobic molecules being right next to each other. So there is no repulsion. But we say this is lipophobic. So why would a hydrophilic molecule be lipophobic? Well, even though there's no repulsion, if this methanol molecule is interacting with this benzene, it's losing out on this stabilizing electrostatic interactions with water. So it is increasing in destability, otherwise known as decreasing in stability. So the most stable spot, and we're going to talk a little bit more about energetics when we hit metabolism. The energetics of this favor methanol interacting with water. So methanol preferentially will choose water to interact with because it's more stable. It is not anything to do with hydrophobic molecules and hydrophilic molecules not playing along. They are indifferent into each other. They will slip right past each other. There's no force forcibly separating them. Instead, it's that water molecules get more stability when they interact with hydrophilic molecules, or hydrophilic molecules get more stability when they interact with water. All of this, we're talking about methanol, but it still applies to water, which is why if you ever mix water and oil, they will separate from each other. That is called the hydrophobic effect. We will talk about it a little bit more when we talk about membranes and proteins. For now, we just need to understand this basic concept. Like likes like. Hydrophilic molecules like other hydrophilic molecules. Hydrophobic molecules, they actually don't really form a lot of stabilizing interaction with hydrophobic molecules. The reason why they interact has to do with this thing called entropy. Once again, that is the hydrophobic effect. We're going to talk about that later. All right, so we've talked about molecular polarity, but now we're also bringing in this idea of interactions between molecules that are electrostatics. And in fact, this interaction right here is a very special interaction called a hydrogen bond. For this to occur, we need this exact setup here. We need a hydrogen with a partial positive. So it's bonded to something, that's what R means, with a partial positive, and it is interacting with something, let's call it A, with a partial negative. Okay, so now we need to ask ourselves, how do we get this? Well, we can sort of break this down into three criteria. The first criteria is we need a hydrogen bonded to an electronegative atom such that St, it possesses a partial positive charge. This gives us the partial positive charge on the hydrogen, but that is only one part. Additionally, we need an electronegative element nearby with a partial negative charge. The final thing that is sometimes skipped over, but it is important, the electronegative element nearby must have a free lone pair, as we've discussed earlier. So let's draw this out. Perhaps we have some molecule with an oxygen and a hydrogen. Remember, this oxygen will have a partial negative. This hydrogen will have a partial positive. Then let's put it, maybe another oxygen that is connected to a carbon and what's called a carbonyl. We don't care about what it's attached to here. This oxygen will possess a partial negative, and it in fact has two lone pairs. This carbon has a partial positive. What that means is this partial positive, did I write positive here? This partial positive on the hydrogen forms an electrostatic interaction with the partial negative on the oxygen, specifically at these lone pairs. So if we wanted to be highly technical, we would move one of these lone pairs and put them here. Now, what this ends up giving us is a donor of the hydrogen bond and an acceptor. In this case, here is our donor. It is giving the hydrogen. This is our acceptor of the hydrogen bond because it is grabbing onto that hydrogen through that electrostatic. Another way to describe this is that we have a polar covalent bond, that oxygen-hydrogen bond right here, giving rise to a hydrogen bond. But these are separate. This bond and this bond are not the same. One gives rise to the other. Now, a very cool thing that you will talk about in Biz 102 is that hydrogen bonds can actually facilitate the movement or the generation of oxygen-hydrogen covalent bonds. It's very, very cool. However, it is beyond the scope of what we will talk about in this class. So sort of slot it away until you reach biochemistry. All right, so we have been building up these ideas of elements. They have different chemical attributes. We can assemble them together to do certain things. And so that's going to bring us into this idea of functional groups. In other words, a collection of atoms that when attached to a larger molecule lend that larger molecule some functionality related to that functional group. There are a few we're going to talk about. Now I'm going to hit all the ones I talked about in discussion. I'm also going to add in one more just because I can. Let's start with the amine. Amines generally look like H2N attached to something else. Remember, this R just means it's something we don't particularly care. However, amines can also look like something else. They can have these hydrogens replaced with other R groups. So they might look like R1 bonded to nitrogen, bonded to R2, bonded to R3. As long as these R groups do not possess a carbonyl, this holds true. Additionally, amines, remember what I said earlier, how they can pick up hydrogens? This can happen here. So if we add in a hydrogen and in the reverse direction, what this is saying is this is our starting. It undergoes this transformation with the arrow after adding in a hydrogen. And now, remember how we showed earlier that when we did this, nitrogen gets a positive charge? That's what happens. In other words, we've added a proton. Remember, H plus is just a proton. It's a hydrogen atom without an electron, which is just a proton. And so we call this the deprotonated state. And this is the protonated state. This can also work down here where we can pick up a hydrogen and carry on. Oop, get out of here, Grammarly. Pick up a hydrogen as well. Now note that amines can also have this last hydrogen replaced with another group, so R4. All right, next we're going to move on to our amides. And amides just sound like a more complicated amine. That's exactly what they look like. Start with our amine, but this time, instead of being attached to an R group, it's attached to a carbonyl. This is important. Okay, this changes the properties of this NH2 group such that it no longer acts like an amine. Once you take organic chemistry and you learn about resonance, you will understand why that is. This amide and its resonant properties is actually very important for protein folding, and we will learn about that in Biz 102. Now, just like our amines, these hydrogens can be replaced with R groups, so you could also see something that looks like this. That is still an amide. Moving on, we can move to our hydroxyl groups. You can also hear these referred to as alcohols. These look like R, O, H. These can be deprotonated, however, we won't discuss that in this class. Moving on, we have our carboxylic acids, or our carboxyl groups. These are our quintessential acids in biology. Just like the amines, these have the ability to gain and lose protons. Here's our protonated form. It has the proton. And here's our deprotonated form. It lacks the proton. All right, the last one is a derivative of the carboxylic acids, and this is the esters. Here, instead of it being an OH, it is an O attached to another group, a non-H. All right, moving on to our next few ones. Oh, excuse me. My apologies. We can start off with the thiol. Thiols, just like alcohols, there's that OL. However, that thio is referring to sulfur. So this has HS bonded to an R. Then we have the thioesters, which think back to the other esters. We have an S, double bond O, and this is attached to R and another R. Next, we have a phosphate. It's centered around a phosphorus, and it's surrounded by 4 oxygens with various levels of protonation. For our purposes, whether or not all 3 of these oxygens are protonated, have a proton, or are deprotonated, they will also be called phosphates. Oftentimes at biological conditions, which is a pH of 7.4, you will see 1 of these protonated and 2 deprotonated, or 2 of them protonated and 1 deprotonated. Finally, our last group is the methyl group, which has our H3C bonded to something else. It is important to memorize these because these will be important when we start building our macromolecules, which is the last step for today. So we have 4 macromolecules. Let's start off with our lipids. Lipids, remember how we said lipophobic was going to be our hydrophilic molecules, and our hydrophobic are going to be lipophilic, and we said these lipophilic molecules are probably going to be nonpolar? That's exactly what we'd expect from our lipids. They're going to be majority carbon-hydrogen bonds. Let's go over a few examples. A common one you will see are our fatty acids. These are composed of a carboxyl group and a long carbon-hydrogen chain, or tail. This is very common where you have the hydrophobic tail and you have a small polar head. You will see many of these come together to make our glycerophospholipids or our phospholipids. We will talk about that when we reach cell membranes. Another common one is cholesterol. This one is going to take a little bit to draw. Bear with me. It is also in my slides. Cholesterol is centered around 3 rings that are 6-membered and then 1 5-membered ring. It also has a group that looks like that. Once again, notice the sheer number of carbon-hydrogen bonds. It is now cyclized. They are now forming rings. However, the majority of this is still carbon and hydrogen. That is the key you're looking for. These large sections of hydrophobic conditions or buildup. Next, we can move to the carbohydrate. This is very conveniently named. Carbo meaning carbon and hydrate meaning water, aka carbon and water. So, for every carbon, for one carbon, we should have one water molecule. The other way to write this is the carbon to hydrogen to oxygen ratio is equal to 1 to 2 to 1. If we were to draw some examples, here is a linear form. This here is D-glucose, where each of these intersections is a carbon. Notice how every single carbon is attached to a water molecule. This carbon down here is attached to a water molecule and an extra hydrogen. That extra hydrogen pops up here, giving the topmost carbon its last hydrogen. Note that sometimes these groups an OH might be replaced with an additional H. This does change the ratio. However, the majority of the molecules still has this 1 to 2 to 1 ratio. So even though some of these groups might change, the parent group remains the same. And it won't ever get to the point where it looks like a lipid, where the majority of the molecule is carbon and hydrogen. We will give one more example. This one is also glucose. However, this is it in its cyclized form, a glucopyranose. Once again, name not important. Notice how even though it's a ring structure, every single carbon still has a water molecule. Now, the monomer for these macromolecules, for lipids, there isn't true monomers because lipids, fun fact, are not technically a macromolecule because they do not possess a true monomer. For carbohydrates, we can link multiple glucoses together. For example, let's draw in this one glucose molecule, and we can link it together with another glucose molecule. This happens many times throughout our cell, including when we're making glycogen, which is a storage form for glucose. You will learn that in physiology, cell biology, and biochemistry. And we would denote the monomer for carbohydrates often as a monosaccharide. In other words, single sugar. For our third one, we will move on to nucleic acids. Nucleic acids are composed of the monomer of nucleotides. A nucleotide is composed of 1 to 3 phosphate groups, a ribose sugar, and a nitrogenous base. We will learn more about these when we touch on genetics. To give you an example of a nucleotide, here's our ribose sugar attached to our nitrogenous base. like that. So large, bulky group containing nitrogens. And then finally, hello, don't do that. Thank you. We can add in our phosphate. This specifically is adenosine monophosphate, otherwise known as AMP. Polymerizing multiple of these nucleotides together, which we will learn how to do that in genetics, will result in our nucleic acids. Finally, we have our proteins. Proteins are composed of the monomer of amino acids. This will be our primary topic next week. Very quickly, our amino acid anatomy. Well, it's an amino referring to an amine group and an acid referring to our carboxyl group. So putting this together, we end up with this structure here. Note that R, when you're discussing amino acids, is actually very important. It is no longer just another group. It is actually the diagnostic group for amino acids. So if I asked you about the amino acid leucine, leucine has a very particular R group. If you're curious, it is CH2CH3 This is different from, say, the amino acid asparagine, which is a CH2 group and an amide. The R group defines the amino acid. You are not expected to memorize any amino acids in Biz 2A. However, we will discuss them in detail next week. Note, when you add amino acids together, you will end up with what's called the NCC backbone. In other words, when you add amino acids together, you will be able to find NCC, 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 referring to nitrogen, carbon, carbon, nitrogen, carbon, carbon, all the way throughout the entirety of the protein. This is a diagnostic feature of proteins. There are non-protein peptides. However, we do not discuss them in this class. All of our amino acids that when put into a polymer, when we're discussing proteins, will be our true, what's called alpha amino acid proteins. So this feature will always hold true for our class. Now, there are many functions for all of these. I did put them in my slides. Our goal is to slowly build that throughout the quarter. Proteins handle many, many things. Like I said, we're going to discuss that next week. Oftentimes, they are responsible for catalyzing reactions. There are a few nucleic acids that also catalyze reactions, including in the ribosome for protein synthesis. Carbohydrates often serve as an energy storage. However, they have numerous other purposes for the cell, including protein modification and cell identification. Lipids also have many, many uses, including making up membranes, storage, hormones, all over the place. Proteins can also be hormones. Once again, a good amount of that we will learn in this class. Some we won't, and you will learn in more advanced biology. But the key feature, the key thing that I want you to get out of today is that all of our biology from here on out will be reliant on the information we learn in Biz 2A.